So welcome everybody. It is a pleasure to have us with us today, Dr. Ioanna Psaradaki from MIT. Dr. Ioanna Psaradaki specializes in high energy astrophysics with expertise in high resolution X-ray spectroscopy. She holds a bachelor's and master's degree in physics from the University of Crete in Greece and earned her PhD in astrophysics from the Netherlands Institute of Space Research in collaboration with the University of Amsterdam. Her research focuses on dust X-ray absorption, scattering, fine structure studies, and photoionization modeling. Dr. Psaradaki has conducted laboratory experiments on interstellar dust, contributing significantly to the development of the most current X-ray dust extinction model. In November 2022, she became a NASA participating guest scientist and joined the science team of the new X-ray imaging and spectroscopic mission. So, Ioanna, please, you can start.
Thank you. Θα μιλάω όσο πιο δυνατά μπορώ. Αν δεν μιλάω δυνατά, να μου το πείτε. Ωραία. Hi everyone in the room and on Zoom. It's really a great pleasure to be here. If you cannot hear me, please speak up because I'm not a very loud speaker, but I'm happy to talk a little bit louder if you cannot hear me. So in this presentation, I'm going to try to describe the work we've been doing over the past few years to understand the chemistry of interstellar dust in our galaxy using X-rays. But first of all, let's set the stage. So with our research, we try to address some fundamental questions in our field. These are, what are the fundamental building blocks of planetary systems? And how does interstellar dust contribute to star and planet formation? In this talk by dust, cosmic dust, or interstellar dust, I mean small solid particles that pervade the interstellar medium of our galaxy and also other galaxies far away. And here you see in this plot a Gaia image of our Milky Way, of our galaxy, and across the galactic plane, it is where all the gas and dust is concentrated. And this dark region, the patches that you see here, basically these are clouds of gas and dust that absorb the light of the stars that are located behind them. And when we study the interstellar dust, we want to understand three quantities. The first is the chemical composition. Basically, this is the chemical elements that make up a dust grain. The second is what we call lattice structure, or simply crystallinity. And by crystallinity, I mean how the atoms in a dust grain, a small dust grain, are organized. So we have an organized network of atoms in some cases, and that's how we call that this is crystalline dust. And in some other cases, when the lattice structure has been distorted, we have amorphous dust grain. We have this chaotic structure of atoms. And the last property of dust that we're interested to understand is the size distribution. And this is basically the physical size of the dust grain. And we know today that dust grains occupy only about 1 to 2% of the total mass of our galaxy. So why is it important to study? Well, there are many reasons why we're interested to study interstellar dust. So first of all, dust provides a cooling mechanism for interstellar clouds where star formation takes place. So it helps star formation because it absorbs the UV radiation, as you can see here, and afterwards it emits this radiation in the infrared. Secondly, it plays a very important role for molecule formation because the surface of a dust grain is a little factory that brings atoms together and then molecules can form. Also, dust has a magic property, let's say, because it aligns with the galactic magnetic field. So here you see an image. This is, if we assume that the dust grain is elongated, the small axis aligns with the galactic magnetic field, and this is very useful because, for example, we can study through optical polarimetry the structure and the strength of the magnetic field in star-forming regions, in molecular clouds. And also, well, sometimes astronomers want to get rid of dust because it's on the way, especially if you want to study the cosmic microwave background. But even in this case, we need to know the distribution of dust in our galaxy, right? And lastly, dust is a very important ingredient to make new planets and therefore new life. Now, what is interstellar dust made of? What are the ingredients that make the interstellar dust? So we know today that there are big 5 elements: magnesium, silicon, iron, oxygen, and carbon. These are the significant contributors of the dust mass. Here you see an image of the Earth's crust, and we see that some of the ingredients that are in the interstellar dust, we basically have them here on Earth, especially oxygen and silicon, that are very important for life. And other elements such as calcium, chromium, or titanium, they're highly depleted into dust, but they're not very abundant, so they're not such significant. And we categorize dust into 2 main groups according to their chemical composition.
Please mute your microphones, please.
That's okay. That's fine. Yeah, I think here.
Θωμά, κλείσε παρακαλώ το μικρόφωνο.
Ναι, ναι.
Εντάξει, ευχαριστούμε. Okay, so what was that? No, that's okay. Yeah, I think. Yeah. All right, so I was saying that dust is categorized into 2 main groups according to the chemical composition. The first is the carbonaceous dust. This is mainly in the form of graphite and PAHs, and silicates. Silicates is a group of minerals, so this is what we're interested into the most, made of magnesium, silicon, oxygen, and iron. And we have 2 very famous groups of silicates, the so-called olivine and pyroxenes. These are the names of these 2 minerals, but what I want you to remember is that the main distinction between these 2 is how many oxygen atoms they carry. So olivines have 4, while pyroxenes have 3. And it's important to understand which of the 2 is dominant in the interstellar medium, because then we can understand what form oxygen takes in our galaxies, it may in gas or in dust. And other than silicates, we also have dust in oxides, such as those. This one has also ferromagnetic properties because dust also has some, is also ferromagnetic. Sulfates, which is some iron bound with sulfur, and as well metallic iron, some pure iron particles in our galaxy. Now, in this talk, I'm going to talk a lot about abundances and depletions of chemical elements. By abundance, I mean how much of an element we have, the amount of an element we have in a specific area. And we usually compare this to some standard values that we usually consider that sun is a good proxy. So we say this is according to the sun, is how much we have according to the sun. And also I'm going to talk a lot about depletion. And by depletion, I mean that this amount of this element is not anymore in gas, but it has left the gas phase, it's now in dust. And is usually defined here, that's an equation, as a logarithm of the gas phase column density of this element versus the hydrogen column density that we have in a line of sight, minus the reference abundance that we have for these elements. But briefly, depletion of an element is how much of it is not anymore in gas, but is now in solids, in dust. And we have some indirect ways to look into elemental abundances and depletions. And this is if we look into interstellar clouds and we see, for example, how much of an element we have in gas phase, and then we compare to the amount that we expected to have according to these standard values, and then we say, okay, we're missing this much oxygen, this much magnesium, so this should be in solids. And here you see this plot, for example, so this is the depletion of an element versus a depletion factor. The depletion factor is simply, if we take a region in our galaxy and we say how much overall all the elements are in dust in this area. So the larger this F star factor is, the more the elements are depleted in a specific molecular cloud. So we see, for example, that oxygen is only mildly depleted into dust, as well as carbon, but magnesium, silicon, and oxygen have a different story because these are this departs significantly from this value here, that it should be the solar value, our reference. So they're mainly into dust form, they're not anymore in gas. So now, in our field, in the field of astromineralogy or astrochemistry, as we say, there are a lot of open questions for now. The first one refers to the oxygen budget problem. So oxygen is one of the most abundant elements in our galaxy. It comes in many different forms: neutral, ionized, molecular, and also in dust. But we yet don't understand what are the reservoirs of oxygen, especially in the dense region, in the dense star-forming regions of the interstellar medium. And this is illustrated in this plot here. This is the oxygen abundance. This is the higher value that we expect to have according to the solar values. And this is density, different density regions in the galaxy. So in the denser regions of the interstellar medium, the combined contributions of silicates, oxides, ices, and here there is CO, maybe I can hide this one. And CO gases cannot account for all the oxygen we expect to see. There is some amount that we don't know where it is. So is it in gas? Is it in dust? Is it in some other form? We don't know yet. Another open question refers to iron. What form iron takes into the interstellar medium? We know today that a large fraction of this element is locked up in dust, more than 90% of it. And we know that most of it comes into our galaxy from supernova type 1a. If we focus on this part of this plot here, it shows the abundance of an element. Most of the iron comes from supernova type 1a, but not from core collapse supernova or AGB stars. But these two have been hypothesized to be very efficient in dust condensation. Therefore, if dust is produced here, then it should deplete into the ISM outside of the usual stellar condensation sources. And the question is, what form does it take if it condenses into the interstellar medium? There are some candidates, of course, in silicates, as I described before. We could have iron in silicates. We could have iron as metallic nanoparticles in the galaxy. Because iron could be also ferromagnetic, we could have also magnetite, this composition, or iron sulfates, iron bound with sulfur. And some of the questions that we're interested to understand is, are the silicates, for example, iron rich or iron poor? And what is the ratio of magnesium to iron in the silicates? Now, high resolution X-ray spectroscopy is really a powerful tool to understand the chemistry of our galaxy. There are some techniques that we use to study the interstellar medium using X-rays. The main is that we have in our galaxy a lot of bright X-ray sources. We use low mass X-ray binaries, usually as the lighthouse. So this is simply a lighthouse. The lights are way into the ISM that has all the gas and dust. And what we observe with an X-ray satellite is an absorption spectrum that it looks something like that. And this absorption spectrum has all the information about the gas and dust that is in the line of sight. But now, observationally, how do we look into the spectral features of gas and dust in the X-ray spectrum? So this goes back to basic physics. I'm sure everybody remembers, but just a brief reminder. So the X-rays are primarily absorbed through the photoelectric effect, right? So what happens is that an atom absorbs a photon and ejects an electron. And this electron has energy equal to that of the photon minus the binding energy of that removed electron. So what we see in the X-ray spectrum is some edges, as we call them, the photoabsorption edges that correspond to the binding energy of the removed electron. And we see them mainly in the K and L shells, mainly in the K. And another quantity that I'm going to talk about in the rest of the talk is the transmission of X-rays and their cross-section. And the transmission of X-rays depends on the column density of the material that we have in the galaxy in a line of sight that we study. And also in the cross-section, which is not more than absorption probability, briefly the probability that we have that some radiation hits a target, let's say. So But how do we study the dust into the X-rays? What are the features of dust in the X-rays? So as I said previously, if we have only gas, what happens is the photoelectric effect. We have this X-ray photon interacts with the atom, so the ejected photoelectron will produce this photoabsorption edge at the binding energy of the removed electron. But in reality, we have dust, right? So we have multiple particles. So the ejected photoelectron will interact with them. And then we will have constructive and destructive interferences because of this interaction. So the resulting cross-section will be influenced by that, and we have these structures around the photoabsorption edge, which are called the X-ray absorption fine structures. And these are the fingerprints of dust. And the shape of these features changes according to the dust chemical composition, crystallinity, and size. And this is what you see here. Here you see the impact of different grain properties on the shape of the extinction and absorption cross-section. Here we have an absorption cross-section of two different types of dust, olivines versus pyroxene, two different chemistries. So here you see the difference in the pattern of the X-ray absorption fine structures. Here in the middle panel, you see the same absorption cross-section, but here you see the same dust grain chemistry, but different crystallinity. You have crystalline versus amorphous dust. The amorphous dust is in yellow. So what we see here is that as the grain becomes more amorphous, more disorganized, then the profile gets smeared out. And in the first panel, you have extinction cross-section. This is different because it also includes scattering. But what I want you to notice is that we compare two different dust size distributions of dust. So here you see that the larger grains that we have in a line of sight in our galaxy, then we have a stronger absorption peak here, which is called the scattering peak. I'm going to talk more about it at the end. And this is an example. This is real data from Chandra X-ray Space Telescope in black here. And this is a photoabsorption edge, a gas model, basically. And you see that the model doesn't fit very well the data because there are the dust features here, these oscillations, that this is what we need to model to understand the chemistry of dust in our galaxy. And one of the advantages that we have by studying the interstellar dust in the X-rays is that because of the nature of the X-rays, because the transmission depends on the column density, on the material in the line of sight, we can study different column density environments through the different photoabsorption edges. For example, if you want to study dense interstellar medium, if you go to column density 10 to 23, we need to go to the iron K edge around 7 keV, or if you prefer in angstrom, this is below 2 angstrom. But if you want to study more diffuse ISM, or even more diffuse in the galactic medium, we need to go to lower energies. For example, if we want to study the diffuse ISM with column densities about 10 to 21, we need to go to the iron L and oxygen K edges. Now, what telescopes do we use? We use Chandra and XAFS Newton. So these are the two telescopes that currently have high resolution X-ray spectrometers. And these telescopes complement each other. Chandra is the NASA mission, and ESA is the European, XAFS Newton is the European one. And this gives us basically beautiful data for 25 years that are now in orbit. So as I said, they complement each other. So this means that their capability to detect weak feature is not the same for every spectral region. So if you want to study iron and oxygen, we need to go to XAFS Newton. As you can see here, this is a figure of merit plot. So this is the square root of the effective area of a telescope times the spectral resolution. Basically, this quantity shows how well a telescope can detect weak lines, let's say that. So here, this is a little higher in the oxygen and iron, this blue line here, which refers to XAFS Newton. So this is where we go to study, especially oxygen. If we want to study silicon and magnesium, we need to go to Chandra because it has higher spectral resolution. Now, this is all great, but in order to study the dust, we need to have models of dust, right, to fit our data. And And we noticed that there is a lack of good models of dust in the literature. So that's why we started a few years ago a series of laboratory experiments when I did my PhD in the Netherlands. So we went to a few laboratories in Europe. We went to the Soleil and ESFR. These are synchrotron beam lines in France. And we also went to an electron energy loss microscope facilities in South Spain, in Cadiz. And I acquired measurements of dust, basically X-ray models of dust from the laboratory to use with our X-ray data. So we had about 20 dust samples of different chemical compositions. We had cosmic silicates with different magnesium to iron ratios, oxides, and as well iron sulfates. Some of them were natural from meteorite, and some of them were synthesized made in a laboratory in Jena. And most of them were in both crystalline and amorphous atomic configuration, so we can also study the crystallinity of dust. Here you see an image of an electron energy loss spectrometer in Cadiz in South Spain that we used. And here are maybe you cannot see very well, the contrast is not great, but you can see these are the dust samples as we carry them in our luggage to bring them to the laboratory. And there is some little powder here inside them. So I'm going to describe in the rest of the talk the experiments and the results from the analysis we did for the oxygen iron, so for the oxygen iron edges. So this is the heart of the electron microscope that we used. So we had these samples, the dust sample. The dust here is this black powder that we locate on a small carbon grid. And this carbon grid, we place it in here in the microscope, and what happens is that there is an electron beam that interacts with the dust sample. And what we observe is the change in the kinetic energy of the electrons from the beam after the interaction with the dust sample. And we have the resulting spectrum from the laboratory, the X-ray spectrum of dust in the laboratory in the oxygen iron edges, as you can see here. And this is a picture of how the dust looks like in the laboratory. And the darker regions are basically regions where the dust is thicker. Now, in order to use these laboratory measurements, we need to translate them to a quantity that is useful for us, right? And this is the extinction cross-section. And we know that extinction by dust means scattering and absorption. So we need to calculate these two components. And in X-rays, we often use a misscattering approximation. So, and in order to calculate the scattering and absorption, we need to characterize the response of a material to an applied electric field here. And this is characterized by the complex dielectric function, as you can see here. And the reason why I say that is because this is useful because what we want basically to compute is the refractive index, the M quantity. So now the refractive index is the square root of epsilon, the complex dielectric function, and it shows how the light propagates into a certain material. In our case, this material is the dust. So we need to find the real and imaginary part to understand how basically what is the response of our dust sample. So from the laboratory, we have K, which is the absorption component of the refractive index, and then we calculate the N, which is the scattering component. And having calculated those two, we can find the efficient scattering and absorption efficiencies, and then integrate over a dust size distribution that we select, and calculate the total dust extinction cross-section. But scattering, basically this is the idea of how we calculate this scattering by small particles. But scattering happens every day, and we see it also in nature, right? Scattering by small particles. So this is a picture from Chios, my home island. And here you see a picture from the sunrise, but also both in the sunrise and sunset. What happens when the sun is very low is that we see all these beautiful colors because the particles that are in the atmosphere, they scatter the visible light. So it's something similar to that, not exactly, but something similar. So as I said before, we have laboratory data, right? Raw laboratory data, and from that we have K, the absorption component of the refractive index, and using some transformation, we find also the real part. So we have N and K, and then using the size distribution, in our case, what we use is this grain sizes. We use some misscattering code, and we calculate the dust extinction cross-section. So this is one example from one of our 20 compounds of a dust extinction cross-section here in blue. And here you see the scattering component and the absorption here. So we do this exercise, this computation for all our dust, and we finally end up with our X-ray models that we are ready to use them to feed X-ray data, which is actually the part I enjoy the most. So what we do is that we select a sample of sources along the galactic plane to study the dust grain properties in the line of sight, and along the galactic plane, because this is where most of the dust is located. So we use low mass X-ray binaries because they have a rather simple spectrum. We don't have emission lines that could complicate the detection of the X-ray absorption fine structure. And this is the sample of sources that we came up with. These are the suitable sources to study the oxygen K and iron L spectral regions, because they have the appropriate column density to have enough optical depth in these energy ranges. We also need to have a lot of availability in the Chandra index and Newton data. This is another criteria for the selection of sources. And we need bright sources so that we have enough signal to noise. And we recently obtained some new data from both Chandra and XMM Newton, so this made our life a little bit easier. So this is an example of a spectral fitting procedure. So here you see Chandra data in the iron region, and here you see XMM Newton data in the oxygen K-edge region. And here you see the transmission of a dust model in green and a gas model in purple. So as you see in the iron region, the dust dominates the absorption because, of course, iron is mainly into dust form. But in the oxygen region, things are a little bit different because we have a lot of absorption from neutral and ionized gas, neutral and ionized oxygen, especially neutral oxygen 1. We also have some oxygen 2 up to oxygen 7. This is the singly ionized form of oxygen, and so on. Okay, so as you see here, but we also have in green some contribution from the dust. So the exercise that we do is that for all the sample of sources I showed earlier, for all of them, we fit these spectral regions with the two telescopes simultaneously with all the possible combinations of dust compounds that we computed from the laboratory measurements. And then we statistically select what is the best fit dust compound, so we can understand what is the chemistry of dust in the line of sight. So we end up with something like that, and we see, okay, this compound is not very, this is fraction, and this is the dust compounds, and we see, okay, these are not very significant, but this seems to be a little bit more significant. So by doing this exercise for all the sources, the results that we found are the following. The dust chemical composition in the diffuse interstellar medium is characterized by magnesium-rich amorphous pyroxene, this mineral with the chemical formula, so it's iron ore. And because we need some more iron, we find that also we need metallic iron, about 10 to 15% of the total amount of iron that we have in the line of sight. We also found the 15% upper limit of crystalline dust. And in the infrared, from infrared studies of dust, it's found that an upper limit of 2% of dust. Now, strictly speaking, we're consistent because we're talking about upper limits. But if there is an inconsistency between the X-rays and the infrared, This is possibly due to the nature of the X-rays. So the X-rays are very energetic, right? So they penetrate the dust grain compared to the infrared that we see the surface. So probably we see some crystallinity in partially glassy materials, that they still have some long-range order of atoms. And the fact that we found pyroxenes, this mineral, as the dominant one is important because it has been also observed in protoplanetary disks, which is a key to understand how new planets are formed. So we can, we also confirm this result. And regarding abundance and depletions of elements, we found that up to 20% of oxygen is in dust form, so it's only mildly depleted, and more than 90% of iron is in dust, so it's mainly into solids. Now, the X-rays is a great way to study the interstellar dust, but if we add the far ultraviolet component of the spectrum, we can understand directly what is the abundance of some elements and iron in the gas form. And this is what we did. So for some sources, we looked into the data, spectroscopic data from the Hubble Space Telescope, HST COS data. We looked into the iron 2, carbon 1, carbon 2, and sulfur 2 lines. These are the singly ionized form of these elements. And what we did is that we measured the ionic column densities of these ions, and also we were able to resolve the velocity shift. So these two lines that you see here, they're not two different lines, it's one line, but because the gas is moving, we have two different velocity components. So from the far UV, we have enough spectral resolution to distinguish two absorption systems in the line of sight. So we found that towards this galactic source, there are two absorbing systems, two clouds, let's say, located at 2 and 4.5 kiloparsec away. And from the UV, we could also measure abundances of elements better, like help to measure our abundance values for oxygen, iron, and sulfur. So this is the value that we found. And these are the reference abundance tables that are in the literature according to the values in the sun. And we see that within the errors, we're mostly consistent with most of them in oxygen and iron. So if we look at sulfur, this is our work and this is the reference. So it's not very good, but I'm going to explain in a bit why this happens. So we take only sulfur 2 here because we don't know where is the rest of sulfur. So we only take the singly ionized form of sulfur. For neutral, we don't know. So now I'm going to move a bit further away from our galaxy. So the results I showed earlier are from our own Milky Way, but there is dust also in other galaxies. And the more active a galaxy is, the more X-rays we have. And in active galactic nuclei, or AGN, most of the X-rays come from the very center, the central black hole. And in AGN, the dust is expected to be around the central black hole in this donut shape region that is called the torus, or the dust torus that is usually called, but also it has been found that it could be also from further out from the narrow line region, which is a region that basically moves slower compared to the region that is in the center closer to the black hole. So what we want to understand is what is the location and role of dust in AGN. And in the literature, it has been hypothesized that, that radiation pressure on dust grains could possibly drive AGN feedback. So basically, dust could be a very efficient source of feedback in the host galaxy from the AGN, because it can drive the outflows. So what we did is that we studied, we did a case study of this active galactic nuclei, NGC 6860. So there are many AGN in the galaxy, but we need to find an appropriate one to study the interstellar dust in the X-rays, because we had to find somebody that is sufficiently bright in X-rays, right? We need to have presence of ionized gas to study the ionized outflows. We need dust filters in both X-rays and infrared, and also in this sight line towards the AGN, we should have minimal radiating and absorption contamination from our galaxy, so we can actually see what's in the other galaxy. That's dust in the galaxy. And this is a high-resolution X-ray spectrum in the iron region from this AGN. And here we saw also the feature of dust. So we performed some photonization modeling. I'm not going to give many details about it, but we included the dust component, and what we found is that in this AGN, the location of dust is near the narrow line region, a little bit further from the center, and the host galaxy much further out from the center of this active galactic nuclei. Now, in the last part of the talk, I'm going to talk about a new and upcoming X-ray missions. And recently, actually, in September 2023, we had the launch of a new X-ray mission, CRISM, X-ray Imaging and Spectroscopy mission. This is a mission that is, so here you see this telescope as it is prepared for the launch in Japan. So it was launched as September 7, 2023. This is the picture from the launch from Tanegashima Space Center in Japan. Is a collaboration between JAXA, the Japanese Space Agency, NASA, with also ESA, ESRA, and University of Geneva. And with CRISM, we will be able to look with much better spectral resolution the energetic universe, basically above 2 keV. So it has two main instruments, extend and resolve. So extend is the soft X-ray imager, and resolve is the soft X-ray spectrometer, and has an energy resolution less than 7 eV at the 6 keV band. So the lifetime is 3 years from the launch, but it's possibly going to be extended. And the energy range is 2.3 to 12 keV. Currently, it's above 1.7, so the real value now is 1.7 to 12 keV, but we hope that we're going to reach this 0.3 in the near future. So I have the honor to be in the science team of this mission, and I can say that there are beautiful spectra from our galaxy and also other galaxies. Now, I'm not able to show right now, but I'm happy to talk about it more at the end. And there is a call for science proposals with a deadline May 15th. So if somebody is interested about that, please come and reach me. And regarding the interstellar medium, we are able to study for the first time the iron K edge in detail. The results I showed earlier, they come from the iron L. This is a softer X-ray band, but from the spectral region, we can really probe the dense interstellar medium, because if you remember what I said earlier, that the transmission of X-rays depends on the column density. So with the iron K that is here, we can study dense interstellar medium. While previously we can study the iron only from here, so more diffuse ISM. So this is something that we're doing now for the first time with CRISM, and this is a spectral simulation. The data show are simulated according to gas, so iron only in gas, this red model, and on top you see in blue here the dust model, so you can see that statistically we're able to distinguish much better with between these two phases. But also with CRISM, we're able to study sulfur. No, oh, sorry. Anyways, and sulfur is one of the essential elements for life. And we know that some of it should be in dust. This is the observed depletion of its elements, so it departs from the zero value that we expect to have it if it's not depleted. But we yet don't know which form does it take. And from the Hubble Space Telescope, from the data, we found that sulfur-2, the singly ionized form of sulfur, accounts for only about 1/3 of the total amount we expect to see. That's why we depart so much from the solar values. So the rest should be either in neutral sulfur or dust. Sorry? Yeah. So the rest should be either in neutral sulfur gas or dust, but sulfur has a very low ionization potential, so it cannot be easily in gas, so it should be in dust. And with CRISM now we're able to access with high spectral resolution also the spectral region of sulfur and understand what is going on with the depletion of this element. And now these are my last slides. In the future, we're going to have new Athena. It's a new X-ray mission led by ESA, the European Space Agency. And New Athena will be the largest X-ray telescope ever built, basically, simple words, because here you see the effective area of the current X-ray telescope that have high resolution X-ray spectrometers. The effective area basically is how effective an X-ray telescope is to collect X-ray photons. So the more we have, the more sensitivity we have. And this is energy, so that you see here is XMM Newton, here is Chandra, here is CRISM, and here is Athena. So we see that we're actually going to do much better in all the X-ray band that we're interested to do, not only ISM science, but AGN, clusters of galaxies and other things. And specifically for the interstellar medium, we will be able to probe with much better spectral resolution the iron KH and study the dense interstellar medium. So you can see here, this is again data simulated with only gas, and on top is the dust models, and we see how clear it will be to distinguish among them. But also we will be able to study the size of dust grains. And the size, so here you see two different dust models on top of Athena simulations. So you see this difference here. This is because the ray data are simulated with larger dust grain sizes. So you see, basically the take-home message from this is that we will be also able to study the size of dust grains in a line of sight towards in the galactic plane. And with that, I think I'm finishing, and yeah, thank you very much. I'll leave you with my tape.
Thanks for a very, very interesting talk. There are already raised hands for questions. Go ahead, Kostis.
Because you talk about abundances, as oxygen, there is a depletion, and also I saw that you compare with solar abundances. The fact is that the sun, you're speaking about solar photospheric abundances, but when you are in the corona, the abundances are modified because of one effect called the first ionization potential effect, where the easiest ionized elements are enriched. So I was wondering if perhaps due to winds of stars, there is an abundance in the interstellar medium that is corresponding more to corona of stars rather than their photosphere. This is taken into account.
Yeah, that's actually very interesting because we use the solar abundance, basically the proto-solar abundances, as a proxy. We don't take it for granted that this is the correct value, but we need to have some comparison, right? So sometimes for oxygen, what we usually find is that it's overabundant. So we find about 1.2, 1.4 times the solar abundance. So that actually is a very useful comment because it could be that. But in X-rays, what we do is that we study everything in the line of sight towards an X-ray source. So maybe you have, you pass through some stellar winds, but then maybe you pass through the intergalactic medium, that the abundances are lower, and then it's kind of the mean of everything that is in the line of sight. But that's, I mean, how much they differ?
Well, there are many components of the corona for the solar wind particle for the sun is the same as the photosphere, but there is a slow solar wind where things are different. And moreover, the sulfur is very peculiar because it is at the edge between the first and the low and high FP effect. So it's a very complex, a full literature with combining measurements from in situ, from spectra. It's a full branch of solar physics.
Okay. I will be interested to know a few of these literature studies. Yeah, thank you.
Yeah, well, let me ask you a question.
Yeah.
In external galaxies that are observed rather face on, we see that dust is not evenly distributed over the disk of the galaxy, but it's concentrated, let's say, close to star-forming regions in the internal region of the spiral arms, in rings, nuclear, inner, etc. So all this dust has the same properties, are the same kind, or it is different properties in different regions of the galaxy?
So what we found, but we mainly studied the galactic plane, is that in the sight lines that we looked into, properties are roughly similar. So the results I showed from the dust compounds, this is an average from all the sight lines, but we also saw that the trend is the same. But this is, of course, for along the galactic plane. But I don't expect that the dust properties are the same everywhere in the galaxy. Because, for example, when we studied silicon and magnesium edges that probe a denser ISM, we found some different type of dust chemistry. So in denser regions, probably, for example, there's more oxygen locked into dust because you don't, maybe like molecular clouds are shielded from UV radiation somehow. So maybe they cannot escape. Yeah. So I think they could differ. Yeah.
Okay. So other questions from you? Go on. Yeah, you have a second
I
one.
was just wondering because I remember that about all their organic material. There's a question of the turning of the polarization plane. It is terrestrial or dependent on the three dimensions of molecules. Is it something that concerns you? Can you measure that?
I'm not sure I get the question. Is it like, you mean on the dust screen, the turn of the...
Yes, I think, some organic material, you can distinguish them in turning the polarization to the light to the left or to the right. And
Right.
it's something about amino oxides, for example, that are different in space from the ones that come from biological material. I'm wondering if there is some similar measurement. Can we measure that? No.
So I think in the X-rays you can...
X-ray.
Yeah. I'm not sure actually, but I'm not sure if you can measure the degree of polarization. You can... I think there is some literature to that, which I don't remember right now, but yeah, I think you should be able to do something like that. Yeah, let me look at that.
Let me check if there are other questions from here. If there is anyone who wants to ask a question, just go ahead. Let's see, raise hands here. It's okay. Okay. If not, then thank you again.
And meeting for